So we have described the derivative of a function at a given point as the slope of the tangent to the graph of the function at the given point. So in other words, what we have said is that if we have a graph, let's say y equals f of x, and we have a point on the graph, so let's say this is the point A, f of a, then the derivative is exactly the slope of the line that if we draw it to pass from the point A comma f of a, it matches the given graph in the best possible way. So we call this the tangent line. And the slope of the tangent line is the derivative, which we agreed to denote by f prime of a. So the obvious question is, how do we define the tangent? Certainly the description that it's the line that fits our graph in the best possible way is not going to take us anywhere. So, and look at this graph that I just sketched here. I don't think that actually my choice of line is that good. Let me see if I can possibly change it. But the bottom line is that no matter how well I try to sketch this line, it's still a guess. And so as to define the derivative as the slope of the tangent of this line is something that is not going to lead us anywhere computationally. So what do we do? What do we do instead? Here's what we do. We say, well, okay, so we cannot find this tangent in any direct way. So we're going to use actually an indirect way. And you know what? There is this principle in analysis that that analysis is the art of inequalities, pretty much, or that an equality in analysis is two inequalities. In any case, here we just use the notion of limit. So the idea is, oops, I destroyed my function, and I keep destroying more. So let me redraw my graph. And the idea is that what we do is we take a neighboring point on the graph. So this is the point, let's say x comma f of x. Some point that is not any specific point, but it's chosen so that x is close to a. So x is close to a. And then we sketch the secant line, meaning the line that goes through the point that is of interest to us and that random point close to a that we chose. And now, so I'm going to call this the secant line between a comma f of a and x comma f of x. And now what happens is that this line has a slope that we can actually determine. What is the slope? The slope of this line, it will be the rise, which is the difference in the y's, f of x minus f of a, over the run, which is the difference of the x's, of the inputs, if you like. So difference of outputs over the difference of inputs. So this is the slope of the secant. And now our understanding is that as long as this number x approaches a, and please be careful, this could happen either from the left or from the right. Here I drew this point x to be on the right of a, but nobody says that this should be the case. It could simply be on the left, it could be on either side. But the point that one needs to make here is that, excuse me, as x approaches a, then the secant turns, and eventually we envision it to become the tangent. It's not going to become the tangent at any point of this process, but eventually we feel that as the secant turns, the tangent will emerge. And so we define, and this is our definition of the derivative, we define the slope of the tangent to be exactly the limit of the slopes of the secant, of these secant lines, as x approaches a. And that's from now on our definition of the derivative. And now we can see how we can pin down the right line that will serve as the tangent line at a given point. It has exactly this slope, and now our job will be to see how we compute these derivatives. And today, we're going to stick to the definition. That is, we're going to do plenty of examples using the definition. So let's start with the first example. And here's what we would like to do. So use the definition of derivative in order to compute f prime of 3, where f of x is equal to x squared plus 1. Okay, let's do this example. So we start by writing the definition. So f prime at 3 will be the limit as x tends to 3 of f of x minus f of 3 over x minus 3. Now we want to plug in everything. So f of x is x squared plus 1. How much is f of 3? If you plug in f of 3, you will find that it's equal to 10 over x minus 3. And please note that when you compute derivatives, you will always come up with a limit which is 0 over 0. Now you can see why we paid so much attention to those limits, because they come up all the time when we try to compute derivatives. So, so this will become the limit as x tends to 3 of x squared minus 9 over x minus 3. And here we have a simple cancellation. So this will be the limit as x tends to 3 of x minus 3 times x plus 3 over x minus 3. And now we can get rid of the two quantities that make that 0. And we will have the limit as x tends to 3 of x plus 3, which is equal to 6. And we can also, even though we were not asked to do that, so I'm going to say, by the way, the equation of the tangent to the graph of f of x at the point, what is the point? The point is 3 and the output is 10. So at the point 3, 10 is a point slope formula. So what does it give us? Y minus f of 3 is known to be 10, is equal to the slope, which is the derivative, meaning 6 times x minus 3. And you know, you can work it out if you like. I mean, we have already been through this. It's not like you have to do it every single time. If you do it, it's fine. If you don't do it, it's also fine. And here's your the equation of the tangent. And just to be on the safe side, let me write here the general form of the equation of the tangent. We have seen this before, but there's no harm in repeating what this equation is. And here's the equation. Okay, and that's it. Okay. Let's do another example. As usual with these examples, it's highly advisable that you pause the video and try to do these examples yourself. So use the definition of the derivative in order to compute f prime of 5, where f of x is square root of x. Okay, so let's see how we do this. Again, feel free, or it is highly recommended that you pause the video and try to do this yourselves. But here's the solution. So f prime of 5 is going to be the limit as x tends to 5 of square root of x minus square root of 5 over x minus 5. And now we can see why knowing how to do the trick with the conjugate quantity is quite useful. So the limit as x tends to 5 of square root of x minus square root of 5 times square root of x plus square root of 5. So we multiply and divide by the conjugate quantity. And this is square root of x squared minus square root of 5 squared divided by x minus 5 times square root of x plus square root of 5, which is going to be the limit as x tends to 5 of x minus 5 over x minus 5 times square root of x plus square root of 5. And here's where we will have a cancellation. So this will give us 1, it will cancel with the denominator, and we will get the limit as x tends to 5 of 1 over square root of x plus square root of 5. And now we can finally plug in 1 over square root of 5 plus 1 plus square root of 5, which is 1 over 2 square root of 5. Again, by the way, this is a derivative that we have not seen in terms of general formula, so we wouldn't have known how to do it. But we can, again, once more, give the equation of the tangent. Which is going to be y minus f of 5, what is f of 5, square root of 5, is equal to 1 over 2 square root of 5. That's the derivative, the slope, times x minus 5. I will not try to simplify this any further. Okay, now, there's a very interesting remark here. There is a variation on the limit that we presented, meaning there is a slightly different way in which we can write this limit. The limit doesn't change. It just becomes a little more convenient in some cases. And here's what we do. Here's how the limit can be slightly modified, at least notationally, not in any essential way. But as you have your function, right? So here's your function. Here's the point a comma f of a, the point we're interested in. And we take a neighboring point. So instead of calling the neighboring point x, so here's a, we actually call it a plus h. So the idea is that we add a small amount to a. And if that small amount h is less than 0, then the point will be on the left of a, the way that I drew it right here. If that amount is greater than 0, then the point will be on the right of a. And now if we write the difference quotient, meaning the slope of the secant line, what are we going to have? We're going to have f of a plus h minus f of a. That's the rise. And what is the run? The run is going to be a plus h minus a. The a's cancel each other, and we get that the slope of the secant is this, which has a slightly more convenient, slightly simpler denominator. And now how do we find the derivative? We have to take the limit of the slope of the secant as the increment h that we have added goes to 0, because when the increment h goes to 0, then the point a plus h comes very, very close to the point A. So we're going to define the derivative as the limit as h tends to 0 of f of a plus h, f of a plus h, minus f of a divided by h. And this is precisely the alternative definition that I was talking about. If you can do a limit using the previous formalism, then you will be able to do it this way and vice versa. So there's no way that you will find any particular example that can be done one way or but cannot be done the other way. But it's just that notationally sometimes this is a little simpler. And let's see an example. So here's an example. Let f of x be 2x cubed plus x. Use the definition of the derivative. In order to compute f prime at, let's say 1. I don't need to have a really big number here. So how are we going to do this? So our solution here will consist in writing the other limit. So we will have that f prime of 1. Let's see what the definition is going to be. It will be the limit as h tends to 0 of f of 1 plus h minus f of 1 divided by h. And this is what? This is the limit as h tends to 0 of, now, wherever we see x, we have to put 1 plus h. So what does that give us? 2 times 1 plus h cubed plus 1 plus h. And what is f of 1? If we plug in 1, we get 3, right? Over h. And now the interesting thing here is once you have this situation, you don't have to worry about any synthetic division or anything like that. You just have to expand the top and do a cancellation, a direct cancellation with the h in the bottom. Let's see how this happens. So to expand the top, I'm going to use my usual identity. Let me write this identity for those who don't remember it. So it's a plus b cubed. What is a plus b cubed? It's a cubed plus 3a squared b plus 3ab squared plus b cubed. So this will become 2 times 1 plus 3h plus 3h squared plus h cubed plus 1 plus h minus 3 divided by h. And here the fail-safe that you will always have, at least in the case of polynomials, is that all the constants from the top should eventually disappear. And here you can see that you have a 2, you have an 1, and then you have a negative 3. And of course, those things add up to 0. So you will have just 6h plus 6h squared plus 2h cubed plus h divided by h. So now you factor out an h. And you get 6 plus 6h plus 2h squared plus 1 divided by h. And this is the upshot of the whole idea. The h's cancel each other. And now all you need to do is just plug in 0. And you see no synthetic division will be needed here. There's no denominator. You just plug in 0 and you get 6 plus 1, which is 7, and that's the derivative. And as we did before, if we want to give the equation of the tangent, that is going to be y minus, what do we say f of 1 was? We said it was 3, is equal to the derivative that we just have found, which is 7 times x minus 1. And that's the equation of the tangent at a given point. I would like to do one more example before we finish this, and let's do a rational function. So let f of x be 1 over x. Use the definition of derivative. In order to compute, let's do f prime of 2. F prime of 2. Okay, why don't we do that? And let's see the solution. Well, same story. So f prime of 2 is going to be the limit as h tends to 0 of f of 2 plus h minus f of 2 divided by h. Now, what is f of 2 plus h? It's 1 over 2 plus h. What is f of 2? F of 2 is 1/2, and we divide by h. We have this composite fraction. Let's clear denominators on the top. So we will have 2 over 2 times 2 plus h. We multiply above and below by 2, minus we multiply above and below by 2 plus h over 2 times 2 plus h. So this way we get the same denominator. And now we put everything under the common denominator on the top. So this is 2 minus, be careful, the negative sign is front of the whole thing. So it will be 2 minus 2 minus h over 2 times 2 plus h over h, the whole thing. And now we make this into a simple fraction. And on the top, the 2's cancel each other. So we have a minus h, and on the bottom we have 2 times 2 plus h times h. And now we cancel. That's the upshot of the whole method always, to get rid of that h. And it's minus 1 over 2 times 2 plus h. And now we can simply plug in h equals 0. And that will give us negative 1 over 2 times 2, also known as negative 1/4. Again, why not give the equation of the tangent? It was not asked in the question, but we will give it anyway. And this will be y minus the value of the function at the specific point, which is 1/2, is equal to the derivative, negative 1/4. It's a negative number. This graph, the graph of this function, will be going down at this point, times x minus 2. And that's the equation of the tangent. And that completes our work for today. Okay, thank you so much for watching.